All right, recording number 3. Third time is a charm. Here we go. This is my data from the modified Atwood's machine lab. I had a system mass of 500 grams, and I'm going to do a whole lot of work right now, not a whole lot, to show you how we can use the slope to figure out that the system mass was 500 grams. All right, so notice what we've got over here on the y-axis, right? This is our y-axis. We've got acceleration graphed as a function of force. That force, if we look in this picture, say, which force are we talking about? Well, it's the net force. Well, what's the net force? Well, it turns out neither of these forces contribute to the acceleration of the Atwood's machine because they are perpendicular to the direction of motion. Right? That big orange arrow shows the direction of motion, and you can see that these forces are perpendicular to that direction, so they're not contributing at all to the acceleration of the system. The only force that is this guy down here, the hanging mass force. So the hanging mass times gravity, mg, that essentially is our net force because it's the only force, right? We don't have to add it with any other forces. The other forces you might be thinking of are the tension forces, but those are internal to the system, right? If I actually model those, right, the strings are pulling on each of the masses, but they're pulling in different directions. So they actually are opposing each other. Internal forces don't cause a system to accelerate, only external forces do, so we won't concern ourselves with those forces. Now, let's take a look at our equation. Net force is equal to mass of the system times the acceleration of the system. What we're going to do is rearrange this equation right here in the form of y equals ax. We're going to do that so we can take a look at the slope, right? The slope being the coefficient in front of the x variable. So let's talk about how we're going to do that. We're going to say, what did we graph on the y-axis? Well, if we take a look back up here, we graphed acceleration on the y-axis and force on the x-axis. So this was our y variable, and this was our x variable. So we need to rearrange it so that the y variable is all by itself. So there it is. We need a equals blah, blah, blah. So to do that, we've got to divide each side of the equation by m. Well, let's use a different color. So we're going to divide each side of the equation by m, right? And now the right side is left with a, and the left side is f over m. Now I'm going to flip the equation around right here just so a is on the left-hand side of the equal sign. And now it still doesn't look like, right here, it still does not look like y equals ax, right? I think ax, a multiplied by x, slope times x, it doesn't look like that. So we're going to take the m and parse it out, right? We're clearly dividing by m. That's the same thing as multiplying by 1 over m. That's the exact same thing. M is still in the denominator. So now I just write 1 over m times net force. So now if we look at the structure of our equation, we have y equals slope times x, where our slope is 1 over m. Don't forget the symbol we're going to use from now on for slope is capital A, so it matches everything there in pivot, and then we don't confuse it with mass, right? Slope is not going to be m anymore. M is always going to be for mass in physics class. So our slope is 1 over m. Our slope calculated from pivot was 1.98 meters per second squared per Newton. So we can set that value equal to 1 over m. 1.98 meters per second squared per Newton. We set that equal to 1 over m, because 1 over m is our slope. All right, now this is a little bit hairy because we've got a fraction inside of another fraction. So let's do a little bit of math to get rid of those, that's the fraction within a fraction. So I'm going to very carefully write meters per second squared over newtons. Now, instead of newtons, I'm going to rewrite Newton as kilogram meter per second squared. Okay, so we still have our numerator and our denominator. So 1 Newton is equal to 1 kilogram times 1 meter per second squared. All right, there's different ways to do this, lots of different math tricks. I'm basically going to say, hey, you know what? I'm going to multiply each side of the numerator by s squared, and I'm going to divide each side, each side of the numerator, each side of the fraction. Divide each side of the fraction by m. All right. You might recognize meters per second squared divided by meters per second squared cancels out. I'm going to be a little more technical, and s squared divided by s squared is 1, m divided by m is 1, and the only thing I'm left with is 1, right? M divided by m is 1, s squared divided by s squared is 1. So in the numerator, I'm left with m, and the denominator, I'm left with kilogram. Okay? If you saw that it was meters per second squared divided by meters per second squared, you could just cancel that out as well. So I'm left with 1.98 divided by kilogram equals 1 over m. Be careful. I think a lot of people might make the mistake of putting the kilogram here in the numerator. It's not. It's in the denominator. So you've got to keep it in the denominator. So now we need to solve for m. Well, we have 1 over m. So to get m, we just flip the numerator and denominator. And we get m over 1, which is the same thing as m. All right, we just flip it. And then we've flipped the numerator and denominator here as well, right? If you do whatever you do one side, you got to do the other. And then we get kg over 1.98. Now, it would be a mistake. It would be a mistake right here if you said, oh, we've got 1.98 kilograms. It's not 1.98 kilograms. 1.98 is in the denominator. So what you actually have is 1 over 1.98 kilograms. You have a fraction of a kilogram. Now, I've rounded the 1.98 to 2 just to make the math a little easier. Right? Please don't do that on your labs. But I'm just proving a point. So 1 over 1.98 is approximately 1 over 2, and that gives me half a kilogram. And half a kilogram is half of 1,000 grams, which is 500 grams, and that checks out. That was the mass of my system. So this is just to prove that we can manipulate the physics equation to get 1 over m for the slope, and then we can set that slope equal to 1 over m, solve for m, and that should match the mass of our system. If it does, then your data is solid.